Hey folks, so this video will be a series of examples going over some of the linear algebra concepts we will need for differential equations. So the first example, let's remember how to multiply a vector and a matrix together. So for this, the key thing to remember is that I'm basically going to be multiplying the rows of the matrix with the column vector itself. And so I'll quickly just highlight sort of the first example. And something I often teach when I'm doing linear algebra class is I'll copy down the matrix. And a lot of times for myself, I find it helpful to draw the vector that's multiplying with that matrix like up a bit. Um, and the reason I do this is because you can sort of line up the dot product that you need to calculate. And what do I mean by that? Well, so if I want to multiply this matrix and vector, the first thing I have to do is multiply that first row by that column as a dot product. So I'm going to do 1 times 1. Right, so I'm looking at 1 times 1 plus 0 times negative 2. Right, it's coming from 0 times negative 2 plus negative 2 times positive 2. Yes. And when I add all those together, I get 1 plus 0 minus 4, which is minus 3. And that's the first component of my resultant vector. For the next component, right, I now move to the second row of the vector. Oh, sorry, the second row of the matrix. Multiply by dot product with that vector. And what am I going to need? I'm going to need 2 times 1 plus negative 1 times negative 2 plus 2 times 2, which gives me 2 plus 2 plus 4. So that's 4 plus 4 is 8, which is the second component of my vector. And one last time, to get the third component, I do the third row of the matrix, dot product with the column vector. And I'm going to get 2 times 1 plus 3 times negative 2 plus 0 times 2. And that's 2 minus 6 plus 0. So that's minus 4. And there you go. That is the final answer to the multiplication problem. When I multiply this matrix and vector, I end up with the vector minus 3, 8, negative 4. Okay. The next question we'll try to solve is how to solve a matrix equation. And so this is the classic AX equals B linear system. I'm given the matrix A, I'm given a right-hand side B, I need to solve for the unknown vector X. Now there's lots of ways of solving this, and the way we're going to solve this in class is to do Gaussian elimination or row reduction in order to find our solutions. So just to remind you, the key idea is that we have 3 row operations we can do. Multiply any row by a non-zero constant, swap 2 rows, or replace 1 row by the sum of itself and another row. And so to solve a system like this, what I can do is set up this so-called augmented matrix. So that just means take your coefficient matrix, the left-hand side, write that down, and then add to this matrix the right-hand side vector B. Okay, so this is now an augmented matrix. It incorporates both the left-hand coefficients as well as the right-hand column vector. Sometimes we'll put a vertical line just to sort of keep track of what came from the right-hand side. It's not necessary, but can be helpful. And now, if you remember, the idea here is to get pivots in our matrix and then use these row operations to get zeros below and then later above those pivot points. So for example, one nice move I could do first here is just swap rows 2 and 3. Or sorry, rows 1 and 2, actually. Right, so if I swap rows 1 and 2, I'll get a 1 in the top left corner, which can be helpful for row reducing. It just makes a lot of our calculations easier. So I'll start by just swapping 2 rows. That's one of my allowable row operations. And now I'm going to use that pivot that we've created in that top left corner. I'm going to get zeros below it using my other row operations. So I'm going to copy down that first row again. So for example, if I do -2 row 1 plus row 2 and use that to replace row 2. This is like the bread and butter move of getting zeros. So what does that look like? Well, I'm going to do -2 times that 1 plus 2 becomes 0. Next, -4 plus 6 is 2. Next, +2, right? So -2 times -1 is +2, plus 1 is 3. And next, -2 times -1, +2 plus 7 is 9. Okay. And I can go ahead and also zero out the 5 below here. And so to do that, I need to do what? I need -5 row 1s, add to row 3 to replace row 3. And so let's go ahead and do that. So that's going to be -5 times 1. So -5 plus 5 is 0. Next, -10 plus 7 is -3. Next, +5 minus 4 is 1. And finally, +5 plus 9 is 14. Okay. So at this point, we have successfully zeroed out below that top left pivot point. And now to continue row reducing, I go to the next row and look for the first non-zero entry. In this case, it's the 2. That's my next pivot, and I'm going to use that to zero out below it. All right, so that I can avoid some, I want to avoid fractions here. So in fact, what I'm going to do is do a little bit of manipulation here. So I'm actually going to start by multiplying row 3 by 2. Okay, so 2 row 3s. And so that's going to give me a 0, -6, 2, 28. And the reason I want to do that is just to make the next step a little bit easier. So now, again, I'm going to zero out below my 2 pivot. And so to do that, I'm going to do 3 times row 2, add row 3, replaced row 3. And so if I do that, here's what I'm going to get. So I'm going to copy down my first 2 rows. Those aren't changing. So the 0 stays 0. So now I'm going to do, like I said, 3 times 2 is 6 minus 6. That's a 0. 3 times 3 is 9, plus 2 is 11. 3 times 9 is 27. 27 plus 28 is 55. Okay. And now look, we're in this wonderful position. I've gotten pivots here, here, and here, right? I've zeroed out below that 2 pivot, and now, again, I'm done with that row. So I go to the third row. First non-zero entry is my pivot. And so I get, in this case, 3 pivots right in a row. And now I can actually start working back up, right? Now that I've gotten to what's called echelon form just means that there's 0 below the pivots. I can now go to row reduced echelon form, which is now to sort of start at the 11 and get zeros above, then go to the 2, get zeros above, and then the 1 is done. And so now I'll have zeros below and above my pivots, right? That's sort of the last part of solving systems. And so let's go ahead and do that. First thing I notice is I can divide everything by 11 in that third row. Let's get some smaller numbers here. So divide everything by 11. That gives me a 1 and a 5. Okay. So like I said, we're going to start with that 1 in the last row and get zeros above it in order to continue our row reduction steps. And so let's go ahead and see what we get. So 0, 0, 1. There's my 5. And so I'm going to start by doing -3 row 3s plus row 2, replace row 2. Okay. So to start out, well, of course, the zeros don't really change anything. 0 doesn't change anything. Here, I'm going to have -3 plus 3 is 0. Here, -15 plus 9 is -15 plus 9 should be a -6. And then I can also, right, while I'm here, I can also use this 1 to get a 0 in the -1 position. So let's go ahead and do that. That's going to be a row 3. Row 3 added to row 1 to replace row 1. So again, the zeros don't change the 1 and the 2. 1 plus -1 is 0. And 5 minus 1 is 4. Okay, wonderful. And at this point, we're almost done, right? So I now have zeros above the pivot. I am now going to get zeros above the 2 pivot. So to do that, for example, I could do negative. I could do a -2 row 2, add to row 1 to replace row 1. So what do I get in that case? Again, the 0 doesn't affect this 1, so that's going to stay 1. Oh, sorry, not -2 row 2, just negative row 2. That's a mistake. So -2 plus 2 becomes a 0. Zeros don't affect these zeros. Okay, so that stays 0. Duh. And now -6, that's +6 plus 4 becomes a 10. Okay. And now I think we're basically home free. At this point, the last thing I notice is that I can just divide that second row by 2 to get 0, 1, 0, -3. And now my matrix is sort of has an identity matrix on the left. And then my solution vector ends up on the right. And so just as a reminder, right, what I'm really looking at here is sort of the x1, x2, x3 components. And so my solution vector x, if that's made up of x1, x2, and x3, well, this is telling me 1x1 is 10, 1x2 is -3, 1x3 is 5, and there you go. That is my solution to this problem. And if you want to check, you could take this vector, plug it in for x and this equation, and it should work out to equality. Okay. Okay, so here's another example of row reducing to solve a system of equations. This time we'll see a little bit more about what can happen. And so the first thing I'm going to do is, given this system of equations, I'm going to translate this to a matrix times a vector, sort of a matrix equation. And so in particular, if I say, let's make our vector x, like capital X, that's going to be a vector with components x, y, and z. And then you might remember that I can do here is take this system of equations and rewrite it as a single matrix equation. So the coefficient of that first row, so that's 1, 3, minus 2. So I'm going to write down 3, 1, 3, minus 2. And then next row, 4, 1, 3. And that last row, 2, minus 5, and 7 times that vector x, right? Now, again, I'll just write it out as x, y, z for clarity. That should equal the right-hand side, which is -7, 5, and 19. And now my claim is, if you go ahead and re-multiply this matrix and vector, you're going to get a three-column vector, right? The first component is going to be the same as this first equation. So, right, so I'm going to have 1x plus 3y minus 2z equals -7. And then same with the second row, same with the third row. Okay, so you're going to have exactly the same equations. So this matrix vector equation is the same as the system of equations. Okay, so now to solve for the unknown x, y, and z, as in the last example, we're going to just do the augmented matrix and row reduce. So setting up my augmented matrix, 1, 3, minus 2, minus 7, 4, 1, 3, 5, 2, minus 5, 7, 19. Okay, I already have a 1 in that top left position. That's very nice for pivoting. And so I'm going to start with a -4 row 1, add to row 2, replace row 2, get a 0 below. Get a 0 below that 1 pivot. Okay, so I'm going to get a -4 plus 4 is 0. I'm going to get a -12 plus 1, that's -11. A +8 plus 3, that's 11 as well. And then -4 times -7 is 28 plus 5. 28 plus 5 is a 33. And let's go ahead and zero out the 2 below as well. So to get rid of that 2, I'm going to do -2 row 1s plus row 3 to replace row 3. Okay, so -2 times 1. So -2 plus 2 is 0. Oops. And then -6 minus 5 is -11. Then +4 plus 7 is 11. And then +14 plus 19. So 14 plus 19 is 33. Aha, how very interesting. So notice at this point, so I've zeroed out below this pivot. I go to my next pivot, and perhaps you notice that if I row reduce at this moment, getting a 0 below that -11, because rows 2 and 3 are exactly the same, they're going to cancel exactly. I'm going to get a row of all zeros when I do that next row reduction. And so I get a very nice looking matrix now. So 1, 3, -2, -7, 0, -11, 11, 33. And then all zeros below when I do the next, the cancellation of the -11 in the bottom row. Okay, so yeah, that's interesting. So in this case, I only have 2 pivots, right? I have a 1 and a -11 pivot. And so because there's no pivot in the third row, at this point, I should continue row reduction by, getting zeros above my pivots. So let's go ahead and do that. So 1, 3, -2, -7, 0, 0, 0, 0. The first thing you might notice is I can really simplify that second row by dividing everything by -11. So it becomes a 1, a -1, a -3. Okay, just make our lives a little bit easier. And as I said, now the goal is to get 0 above that 1 pivot that we had before. Okay, so to do that, what am I going to do? I'm going to do -3 row 2s plus row 1, replace row 1. Okay, so that's going to give me, okay, well, I should start here. So the 0 doesn't affect the 1 above it, so that's going to stay a 1. -3 times 1, so that's -3 plus 3 is 0. Then +3 -2 is 1. And then +9 -7 is 2. Okay. At this point, I have completed my row reduction. I have zeros above and below my pivots. And so let's write down our solution vector at this point. So again, remember that this represents x, y, and z as my coefficients. And so if I were to take what I have as a matrix and return to a system of equations, we end up with a system that looks like this. So I really have x plus 1z equals 2. I have 0x, 1y minus z equals -3. And in that bottom row, I don't have any equation for z. And this is the situation where we say, well, z is a free variable. In fact, z can be anything. And this is the situation where we'll have infinitely many solutions to our equation, right? For each different z value, I'll get different x's and y's. Okay. So what is typically done in practice here is to not leave this as a system of equations like this, but instead to actually solve for x, y, and z, sort of write down a nice parametric form of this solution. So let's go ahead and do that. So what I'm going to do is just solve x equals 2 minus z, y equals -3 plus z, and okay, still z is free, so I don't do anything with that. And to write this as a vector, just remember that my vector x had the components x, y, z. So all you have to do is plug in for x and y, because those have equations, the equations to the left here. So if I plug in x equals 2 minus z, y equals minus 3 plus z, and then z is free, so I can't do anything to it. I just leave it as z. I can take this vector and split it into pieces, sort of the z piece and the non-z piece. And so I have, for example, a 2 minus 3 and a 0, because there's no like constant term in the third component, plus minus z plus z and plus z. And typically what we do is write this as 2 minus 3, 0, plus z times the vector minus 1, 1, 1. And now all of our solutions are of this form. It's this constant vector plus z times this other vector. And again, no matter what z you give me, that does constitute a solution. There's infinitely many solutions here. Z can be any real number. Okay, so this is what it looks like when you row reduce and you have a free variable. Okay, so the last concept to review are eigenvalues and eigenvectors. So just to remind you the definition, let A be an n by n matrix. In other words, it's a square matrix. So if V is a vector that is non-zero, such that there is some real number lambda satisfying this equation. So this is the key equation. In fact, both of these equations are sort of equivalent. They both say A times V equals lambda times V. And the thing to remember here is A times V is a matrix times a vector, but lambda times V is just a scalar times a vector. Okay, so, but if you can find me a lambda and a V that solve this equation, well, we say that V is an eigenvector and lambda is the associated eigenvalue. So the thing to remember here is that we really do need V to be a non-zero vector. And why is that? Well, look, if I allow V to be 0 in either of these equations, it's always true, no matter what lambda you gave me, right? Because I'm just going to get 0 equals 0. And so we really require V to be non-zero because I'm looking for like a non-trivial solution to this equation, right? Which lambdas allow me to solve this for non-zero V? Well, the thing to remember here, this key insight is what helps us come up with a solution method to find eigenvalues and eigenvectors. Because I want a non-trivial solution, that means I want infinitely many solutions to this equation. That must mean, this matrix equation, A minus lambda I times that vector V equaling 0, this must have infinitely many solutions, which means that matrix in front, A minus lambda I, must be non-invertible, must be singular, and must have 0 determinants, right? So these are all different ways of saying the same thing, right? To get non-trivial solutions means that this coefficient matrix must have 0 determinant. Okay, and that gives you a method of starting to find those eigenvalues and eigenvectors. So this is really the key equation to remember. To find the eigenvalues of the matrix, we need to set up this equation, which is often called the characteristic equation. And you actually might recognize this terminology, right, from when we were solving for the solutions of higher order ODEs. And yes, they are related, it turns out. Yeah, there's a way of thinking about how these are the same equation, it turns out. But anyway, so let's go ahead and use this and set up the eigenvalues and eigenvectors of a given example. So if A is the matrix 2, 1, 1, 2, first we need to find our eigenvalues. So that means I need to set up my characteristic equation. The determinant of A minus lambda I equals 0. Okay, so as a reminder, so let me go ahead and just calculate, right? A is the matrix 2, 1, 1, 2 minus lambda times I, remember here, depends on the context. It's always the identity matrix, which means it has 1s on the diagonal entries and 0 everywhere else. So for a 2 by 2 matrix, that's just 1, 0, 0, 1. And so that's my A minus lambda I. And so if I were to combine those, it's 2 minus a lambda, 1 minus 0 lambda, so that's just 1. 1 minus 0 lambda, that's a 1. 2 minus 1 lambda. That's 2 minus lambda. Okay. So that is my matrix A minus lambda I. And so what I need is to set up my characteristic equation, I need the determinant of this matrix, 2 minus lambda 1, 1, 2 minus lambda, set equal to 0, and solve for the lambdas that make this happen. Of course, we have a really nice way of calculating determinants for 2 by 2s, this sort of cross multiplication idea. And so I can calculate the determinant by just doing 2 minus lambda times 2 minus lambda. So that's 2 minus lambda squared, minus 1 times 1, that's 1, and set that equal to 0. Sorry. Okay, so in general, the way to approach this is to expand and factor and solve for lambda. So let me go ahead and do that. So let me get a lambda squared minus 4 lambda plus 4 minus 1 equals 0. Right, so these first 3 terms are coming from expanding this quadratic. And simplifying, I get lambda squared minus 4 lambda plus 3 equals 0. And this looks like it factors. Lambda minus 3 times lambda minus 1 equals 0. Yep, that looks like it works. And so I get 2 roots. I get lambda equals 3, lambda equals 1. And hey, those are my 2 eigenvalues in this case, lambda 3, lambda 1. Let's go ahead and find the eigenvectors associated to these lambdas. In fact, I'll just do one of them and I'll leave the other one for you to find yourself. It's the same process either way. And so let's do the lambda equals 1 eigenvalue, and let's find the associated eigenvector. And so remember, the way to find the eigenvector just means you're solving A minus lambda I times V equals the 0 vector. Okay, and I need to find the unknown V. And so to do that, well, I can set up my coefficient matrix. So it sometimes is helpful just to write down, right? A minus 1 lambda, so lambda is 1. A minus 1 I, so that's 2, 1, 1, 2, minus 1 identity, so that's just the identity. So my coefficient matrix is 2 minus 1 is 1, 1 minus 0 is 1, 1 minus 0 is 1, and 2 minus 1 is 1. Okay, okay, 1, 1, 1, 1, fine. And so my equation is 1, 1, 1, 1 times V equals 0. Well, the 0 vector in this case is just 0, 0, right? Because there's 2D, 2 dimensions. And so just like we did before, I'm going to set up my augmented matrix, solve for my unknown V. So 1, 1, 1, 1, 0, 0, row reduce. And like we've seen before, because I have a pivot in the top left, I can zero out below it, but because the first and second rows are identical, when I get a 0 below that 1, actually everything's going to cancel. And so I'm going to get 1, 1, 0, and then all zeros below it. Okay, so I should have a free variable. In fact, you always should have a free variable when you're calculating eigenvectors, because you really do want infinitely many solutions here. Okay. And so again, if I let V be the vector v1, v2, then remember I'm sort of looking at v1, v2 columns. And so when I translate this row reduced matrix back to equation form, I'm saying v1 plus v2 equals 0, and there's no pivot for v2, so v2 must be a free variable. And because when I'm looking for eigenvectors, I want to write it in vector form, let's go ahead and translate this back to v, which is v1, v2. Now, from before, well, I know v1 equals minus v2, so I can plug that in. Minus v2, and then v2 itself was free. And if I pull out that v2 as the free variable, I'm left with minus 1, 1. Okay. So now technically, no matter what v2 you give me, that would be an eigenvector. So if I take v2 to be 1, I get minus 1, 1. If I take v2 to be 2, minus 2, 2. These are all different eigenvectors. In practice, you only really need one of them. So I'm going to go ahead and say, well, if I take v2 to be equal to 1, I obtain the specific eigenvector minus 1, 1. And that's the eigenvector corresponding to lambda equals 1 eigenvalue. Okay, so you can do the same process for the lambda equals 3 eigenvalue, and get a different eigenvector there. Okay. So hopefully that rings some bells. And if you have questions, please, please, please come talk to me. If you want extra practice problems for these ideas, all of the things I've been going over, you can check Appendix B of your textbook. There's a lot of extra practice problems. So again, come talk to me if you have any questions. And I hope this was helpful.